Welcome to This Explainer. Today, we're jumping straight into the very foundation of the cloud. We're going to break down the three fundamental storage types that are literally powering every single cloud application on the planet right now. Whether you're building on AWS, Google Cloud, or Azure, mastering these three pillars, well, that's exactly what separates the good architects from the truly great ones. Let's get into it. Now, think about this for a second. Have you ever used AWS S3 to host an image? Or I don't know, maybe mapped a shared network drive at the office? Or even just plugged a standard external hard drive into your laptop? If you answered yes to any of those, well, congratulations, because you've already interacted with these fundamental storage technologies in your everyday life. Our goal today is to pull back the curtain and show you exactly how they actually work under the hood.
So here's our roadmap for today. First, block storage and its raw capacity. Second, file storage for shared access. Third, object storage and its infinite scale. And finally, number 4, the ultimate storage showdown. All right, section 1, block storage raw capacity.
To really wrap your head around block storage, I want you to imagine your data being chopped up into equally sized chunks. And yeah, these are literally called blocks. Each of these blocks gets its own totally unique address. The absolute crucial thing to grasp here is that the operating system talks directly to those blocks. It has zero awareness of files or folders at this level. Just picture a blank, brand new hard drive you just plugged into your laptop. You have to partition it, right? You lay a file system over it, and only then does it actually understand what a file even is. Block storage in the cloud works the exact same way. It is just raw capacity. Your operating system has to do all the heavy lifting to add that file system abstraction.
Now notice the huge emphasis here on speed. Because it's such a primitive, low-level technology, block storage offers extremely low latency. We're talking microseconds to milliseconds here. It's blazing fast. Typically, a block volume is attached to just a single server at a time. It's essentially a virtual hard drive dedicated to one single machine. You format it yourself using file systems you probably know, like ext4, NTFS, or XFS. And if you're working in the cloud, you definitely know these as AWS Elastic Block Store, or EBS, Google's Persistent Disk, or Azure Managed Disks.
Let's look at the logical steps you'd actually write in code or punch into your terminal to use this. First up, you create the volume, let's say a 20 gigabyte GPv3 volume on AWS. Second, you attach it to your specific virtual machine, like an EC2 instance. But wait, you can't use it just yet. Third, you have to SSH into that instance, format the device with something like ext4 using the mkfs command, and then mount it to a local directory. Finally, you add it to your server's fstab file. Why? So that if the server reboots, the drive automatically remounts itself. You're basically treating it exactly like a physical piece of hardware. So the big question, when do you actually use it? Well, because of that ultra-low latency we talked about, block storage is your absolute best friend when you're spinning up a production relational database. Think Postgres or MySQL. It's also exactly what you use for your virtual machine boot disks. Bottom line, any workload that demands those sub-millisecond input-output operations per second, or IOPS, absolutely belongs on block storage. Moving right along, Section 2, File Storage, Shared Access. So building a layer of abstraction right on top of that block storage, we get file storage. It basically operates like a massive filing cabinet sitting smack in the middle of a busy shared office. Everyone in the office has a key. Everyone looking at the cabinet sees the exact same folders and the exact same files. And, super importantly, whoever opens a drawer and grabs a file first gets a lock on it until they're totally done. Under the hood, this uses standard network protocols like NFS or SMB to magically manage all that shared access across different machines. The absolute killer feature here, without a doubt, is multi-client concurrent access. Multiple servers can mount the exact same share simultaneously. It maintains a standard POSIX-compliant hierarchy, which just means you get your standard directories, user permissions, and symlinks exactly like you would on a local machine. Plus, the managed cloud versions of this, like AWS EFS, Azure Files, or Google File Store, they automatically scale your storage capacity up and down on demand as you add or remove files. It's pretty amazing. Architecturally speaking, utilizing file storage is just incredibly powerful. First, you install your network file system utilities on your virtual machines. Then, you mount that single target endpoint to a local folder on your servers. Once you do that, any code, let's say a Python script, running on any of those connected servers sees the exact same files instantly. If server A writes a brand new sales report to the shared folder, server B can immediately run a script to read that exact same report. No syncing required. Basically, whenever your workload requires multiple nodes to read or write data at the exact same time,
file storage is your answer. It absolutely shines for things like shared home directories, running content management systems like WordPress, or feeding data to multiple GPUs in parallel for machine learning training. Oh, and it's also the perfect drop-in replacement if you're doing a traditional lift and shift of an on-premise network-attached storage system straight into the cloud. All right, Section 3, Object Storage, Infinite Scale. Now, this is where the cloud completely blows the doors off traditional architecture. How? By throwing away the file system entirely. Object storage is honestly fascinating. Instead of folders and nested directories, your data is stored as flat objects in a massive, globally distributed key value store. It's like a gigantic postal warehouse. You drop in a sealed package, that's your data, and you get a tracking number back, that's your unique key. When you want your data back, you just hand them the tracking number. The warehouse doesn't care if that package contains a letter, a hard drive, or a literal piano. An object simply consists of your binary data blob, the unique key representing its path, and some attached metadata. That's the whole shebang.
Because it totally drops the heavy overhead of a traditional file system and relies entirely on HTTP REST APIs. The scale you get here is just mind-boggling. We're talking infinite scale, literally into the exabytes, with zero pre-provisioning required. You just start uploading, you use simple get, put, and delete web commands. You could also attach really rich custom key value metadata to your files. And thanks to this clever architecture, it is by far the cheapest storage per gigabyte, period. The heavyweights you'll see in this space are AWS S3, Google Cloud Storage, and Azure Blob Storage.
When we look at the code logic to actually interact with object storage, say using an SDK like Python's Boto 3, you're going to notice something totally different. You aren't mounting anything to a server. You simply make web requests. You create a globally unique bucket. Then you upload a file directly to that bucket, maybe attaching some custom JSON metadata, like, I don't know, the user ID of whoever uploaded it. You can even generate a secure, temporary, pre-signed HTTP URL to let someone else download that specific file securely. Oh, and you can enable versioning, so even if an object is overwritten, the previous version of that data is never lost.
However, infinite scale definitely comes with some massive trade-offs. Object storage relies on eventual consistency in some scenarios, and crucially, you cannot do random byte range writes. What does that mean? It means if you change even one single character in a text file, you have to rewrite the entire object from scratch. Because of this, you must absolutely never use object storage to run a database backend or a VM boot volume. Instead, use it for things like media files, massive backups, data lakes, hosting static websites, or storing massive machine learning datasets.
Okay, moving to Section 4, the ultimate storage showdown. Let's figure out how to choose the right storage.
I want you to think of this matrix as your ultimate architect's cheat sheet. Look at the access methods here. Block gives you raw blocks for a single machine. File gives you shared network paths for multiple machines. An object? That gives you standard web URLs accessible from the entire internet. Notice how the extremely low microsecond latency of block storage contrasts directly with the infinite scalability of object storage. And look at the cost gradient, too. Block is the highest cost per gigabyte because you're paying for premium performance hardware. File sits comfortably in the middle. An object is the absolute lowest cost for mass storage. It's really just a perfect spectrum of trade-offs. Look, if you remember only one single thing from this entire explainer, please let it be this exact decision framework. And this applies whether you build on AWS, Google Cloud, Azure, it doesn't matter. If your application needs raw IOPS and only one server is touching it, go Block. If a bunch of servers need to read and write to a shared file system concurrently, go File. And if you need massive scale, global HTTP access, or you're just storing blobs like images and backups, go Object. It's really that simple.
Understanding these three distinct paradigms, and more importantly, their specific trade-offs, is genuinely going to make you a much sharper cloud architect. But here's something to chew on. As AI models start demanding faster and faster access to increasingly massive data sets, the rigid lines between these storage types, they're really beginning to blur. So how will your architecture adapt when exabyte scale suddenly requires sub-millisecond latency? Thanks so much for learning with me today. Keep exploring, and I'll see you in the next explainer.